last time we looked at this, at the language 0 to the n, 1 to the n, for n greater than or equal to 0, and we proved that that was not regular. And the whole idea of this was to say that if it was regular, then there's some, well, we'll take n greater than p. P is the number of states in the supposed or assumed DFA that recognizes B. The book calls this language B. And then we said, well, now consider the string 0 to the p plus 1, 1 to the p plus 1, something like that. Anyway, a string that's long enough, okay? And then we said that if you look at the accepting path, if you assume that that this is accepted by this finite state machine, then that computation has to loop back to some state, some point between the start and the final. Because the machine only has p states, okay, and the length of the string here, well, you have p plus 1 zeros alone. So certainly you have to loop back to some state that you've been to starting from the beginning. And then we're going to break up S. So S is being described as the computation goes along here. S is being consumed. If we look at what's on each one of these edges when we do a transition, we're consuming one more character each time. And then we said we can break up the description of the string into X, Y, and Z. And this is going to be the very first loop that happens in the computation. It's the very first time that it loops back. So we know a number of things about X, Y, and Z. Well, for one thing, S is equal to X, Y, Z. Okay, that's just a description of what S is. And we know that the looping back has to happen within the first p plus 1 transitions. Or the book is a little sharper on this, but it doesn't really matter, and I find it really annoying. I think they would just use p here and then argue that the number of characters that you actually see is always one less than the number of states you go through, and you always have this off by 1 situation. So I just make I make this exponent big enough that we don't have to worry about those little details. So certainly, by the time you've gone through p plus 1 states, you've looped back, and x, y, therefore, is less than or equal to p plus 1, something like that. And that means that that xy just contains 0. So xy just contains zeros. We're not even into the part of the string that has 1s yet, okay? And then we said, well, now consider the following string, x, y, y, z, okay? And we argued two things about that. We argued that, yes, that should also be accepted by this same finite state machine, the supposed DFA that recognizes B, because its computation would just be x followed by the y. That's what consumes this xy. But another loop around here will consume the next copy of y, okay? And then it can follow from there the path that consumed z and end up in a final state. So under one view of this, by looking at the supposed DFA for B, x, y, y, z would be accepted. Okay? But the other view is X, Y, Y, Z shouldn't be in the language B, right? Because X, Y only contains zeros, which means that Y only contains zeros, which means that X, Y, Y now contains more zeros than ones, because the ones are all in the Z part. Okay? X, Y, Y, Z has more zeros than ones. So X, Y, Y, Z isn't in what we've defined B to be. Okay? Well, this is a contradiction. A string can't both be in the language B and not be in the language B. So how did we get into this predicament? It's a proof by contradiction. Way back at the beginning, we made an assumption, and then we did some logical deductions from that point and got into this contradictory state. And so the resolution of that kind of contradiction when it happens is to go back to the beginning and say, what did we assume? And therefore, this assumption cannot be true. So we started out by the assumption that there is a DFA that recognizes B. Namely, or another way of saying that, we started out with the assumption that the language B is regular. And that drove us to this weird situation, this contradiction, and therefore, in the end, we have to conclude that B is not regular. Okay? Any questions on that? That's a review of what we did last time. Okay? And it is a particular proof based on this language which incorporates the kind of thinking that goes into what I'm going to do next, which is called the pumping lemma. So we're going to abstract away from this particular argument and make it a little bit more general. And then having that under your belt, having that general tool under your belt, you can prove additional languages are not regular by appealing to the pumping lemma rather than having to spell everything out here. Although it's often not much of a shorthand, not much of a shortcut. Okay, so here's the, by the way, this is on page 70. No, page 78. This is the pumping lemma. And it says the following. If A is a regular language, okay, then there is a number P. Okay, so this whole field, in my opinion, is overly mathematical in the sense that it says things in ways that are overly general, and you could be a lot more, it would make a lot more sense if you were just more specific. So the pumping lemma starts out by saying there is this number P, and it has these magical properties, blah, blah, blah. But then in the proof it says, oh, let's just let P be the number of states in the supposed DFA. You know, so why didn't they put that in here in the statement of the theorem or the lemma? They could have just said, let P be the number of states, but they didn't. Okay. Whereas over here I did, and I actually said, well, let's let our number is going to be P plus 1. Okay, at any rate. There is a number P, and I'll put my editorial comment here. Almost always. I just say that it's always in my experience, but I'll put it in almost in case somebody who watches these videos years from now knows a language where it's not. Then I'll say, well, yeah, I said almost. I'm safe. Almost always the number of states in the supposed DFA that recognizes A. Okay, so there's some number P such that if a string is in A and that string is long enough, okay, then S can be divided into 3 parts, X, Y, and Z. So, such that S equals X, Y, Z, and what? 1, for all I greater than or equal to 0, X, Y to the I, Z is in A. Okay. 2, Y is greater than or equal to 0. And 3 needs more room. Move this up a little bit. 2, Y is greater than or equal to 0. And 3, XY is greater than or equal to P. Okay? That's it. That's the statement of the pumping lemma. Okay, we're going to have to do something to prove it in a minute. But so we're saying if A is a regular language, then there's some number P, such that if S is any string in A, and S is long enough, bigger than P, bigger than this magical P, but the magical P is almost always the number of states in the DFA that accepts A, then S, the string S here, can be divided into 3 parts, X, Y, and Z, such that S is equal to X, Y, and Z, and the X, Y, and Z have this property, or these following properties hold. This upside down A, by the way, is mathematicians' way of saying for all, okay, because most mathematicians are dyslexic. Now, anyway, that's the upside down A is for all I greater than or equal to 0, for any I greater than or equal to 0, X followed by that number of I's, that number of Y's, sorry, is also an A. Okay? And the length of Y is greater than or equal to, the length of Y is greater than 0. That's important. That Y really exists. You can't make Y epsilon. Y really exists. Okay, Y is greater than 0. If you take that away, anyway, that's essential, that Y is greater than 0. And that XY is greater than or equal to P. Because that first part has length greater than or equal to P. Yeah?
I think it should be less than or equal to P. In the book, that's what it says. That third piece.
Oh, this one, yes. Right. The third one, yeah. Thank you. XY less than or equal to P, of course. Yeah. Which is what we saw over in this example. Yeah. Okay. So this, if you can parse it, if you can fight your way just through the notation here and just read what it's saying, is pretty much what was going on over here. Okay, we had a particular language, B, now we're saying abstractly call it A, and here's the language, and then I'm going to take a look at strings that are bigger than, here P is the number of states. I'm setting P to be the number of states, okay, and I take strings that are greater than, have length greater than P. Well, here it says strings greater than or equal to P, and I could have done that over here too. I could have made this argument. Just, if I make it equal to P, then I'm relying on the fact that when a machine goes through P states, okay, it's actually consumed P minus 1 characters. So if the machine goes through P characters, it must have gone through P plus 1 states. Okay, but there's only P states, so it must have looped around. All right. As I mentioned earlier, by by cutting things so close here, you always have to add in that extra little plus or minus 1, which I find very annoying. So personally, when I do these proofs, I just make the string big enough that you don't have to worry about the boundary conditions. But anyway, we can do that. And so for a string that's bigger than or equal to p, we suppose that there's a DFA that recognizes it. We're assuming that this is a regular language. And then we're considering some other string. And again, here, well, just in order to show that this will lead to a contradiction, we're picking a particular string in this language that's going to lead us to a contradiction. Okay? So we pick that one, and this over here says whatever one we pick, we should get into a problem. These things should hold. Okay? And here we're just picking one that's particularly convenient to make the proof work. Okay, come to the contradiction. And that's, when you apply the pumping lemma, that's something that you often have to do. You have to pick your S judiciously in order to use the pumping lemma to run to a contradiction. Okay, so here we're picking a particular S. We're making this argument that S is equal to X, Y, Z, and there's this loop in here, because the string length is so long that relative to the number of states that you have to loop back like that. And then, in fact, the way we picked this string, xy is less than or equal to p plus 1, I could pick it, so I can say xy is less than or equal to p. That'll conform to that. This would all have worked. I'm just saying if I make this absolutely identical to what the pumping lemma says, it would all have worked, but we'd have to stop every once in a while and say, remember that if the machine goes through p states, it's processed p minus 1 characters. If it's processed p characters, it's gone through p plus 1 states, etc. Now you consider this doubling. Well, this is just I equals 2. The pumping lemma says that for any number of I, all right, even 0, and you can see that. X, now omit this loop and go to Z. That means that I was equal to 0, okay? So X to the 0, sorry, Y to the 0 is just the empty string. Or Y could be 2 or 3 or 17. It's just how many times you want to go around this loop, okay? And xy is less than or equal to p. We saw that over there as well. So the proof that we followed here to run into a contradiction to show that this was not regular is following the game plan of the pumping lemma, which says that if it is regular, this stuff better hold. And what we saw over there is when we did this, x, y, 2, z was not regular. Okay? It was not in A, right? It was not in B. Right? So that would then contradict the pumping lemma. All right. This is confusing, I know, that we're using the pumping lemma in particular over here in this proof to prove that the language B is not regular because we're following basically the prescription here and running into a contradiction. So this says if it is regular, all of this has to hold. And when we tried to make all of this hold, we got a contradiction to X, Y, Y, Z being in that language. Okay? All right. How do we prove this? How do you prove this theorem? Well, the book actually does it two ways, or it says a proof idea, and then it gives a formal proof, which, in my opinion, is just the same thing with a little more verbiage, but it's not essentially different. And in essence, it's just following this same kind of idea, but abstractly. Instead of, well, in fact, I did this abstractly. I didn't, when I showed you this picture, we weren't using the fact that this is my language in particular. Okay, we weren't using this as the particular language. We were just saying this language is accepted by is recognized by some DFA. Okay, now consider the computation on some string which is long enough, some string. Okay, so we'll do it over here. So we're assuming that A is regular. Okay, so this is a proof, or a proof idea. Assume A is regular. Okay, so there is some DFA M that accepts A. All right. The lemma says there is some magical P. Well, in my proof, let P be the number of states of A. Okay? And not of A, of M. Okay? So there's some DFA that recognizes A. All right? We want to show the following properties hold. So suppose S is a string that's in language A, and it's long enough, greater than or equal to P. Its length is greater than or equal to the number of states in the finite state machine that accepts A. Okay? Then I want to show, I'm trying to prove this pumping lemma, I have to show that S can be divided into 3 parts, X, Y, Z, such that these properties hold. Okay? So how do I do that? Well, you consider, so this is just some S, arbitrary S, that is long enough. Now consider the computation of M when it accepts. Of course there's a computation of M that accepts S, because S is in that language A. Okay? And we'll just look at it. Okay? That computation goes through various states, but the length of S is longer than the number of states in this finite state machine. Okay? So it has to loop back somewhere. So this must loop within the first, and here's where this is where this kind of thing annoys me, that they're being so tight, because now you have to think a little bit. It has to loop back within the first, how many transitions? Transitions is a move on an edge. Well, you have P states, right? And if you do K transitions, how many states have you visited? K plus 1, right. Okay, so you must loop within the first P minus 1 transitions. Right? If you have P minus 1 transitions, or if you've seen P minus 1 of the characters of the string, then you've seen P actual states. Okay? Now I'm off by 1. See, I don't like being so precise here, because then you always have to... Yeah. You must loop within the first P transitions, because if you do P transitions, then you've processed P plus 1, P characters, which means you visited P plus 1 states. But you only have P states, so you have to have looped back at least once. Okay. All right, so you must loop within the first P transitions, All right, so you're here, and then you go on after that looping, finally to accept. Maybe you loop some more. All right, that is what we know about the computation when m accepts s. Okay, so I'm going to let this be x. The characters that the computation sees before it enters the repeated. Let's call Q the repeated state. Let Q be the first repeated state. Okay. So we have the computation, the part of S that's consumed in the computation up until the point when Q is first visited. Then we have Y, which is the part of the string which is consumed until Q is visited again. And then we have Z. We should remind you of what we did in particular over in that language, right? So this is how we're dividing. S equals X, Y, Z. Okay? So we're trying to prove that when S is greater than or equal to P, then S can be divided into 3 parts X, Y, Z. Well, we've divided S into 3 parts X, Y, Z, such that S equals X, Y, Z. Oh, so far so good. We only have this little part to go. Okay? For all I greater than or equal to 0, X, Y to the I, Z is in A. Is that satisfied? Yeah, it's satisfied by this construction, by this computation. We can do X. Now, if you set I to 0, it means this is gone. So Y to the 0, that's gone, followed by Z. That's accepting. Okay, so that's an A. What about when Y is equal to 1? Well, that's what we started with. What about when Y is equal to 2? Here's X, Y equals 2, followed by Z. Okay? So for all I, X, Y, I to the Z is also an A. Okay? So that's satisfied. Is Y bigger than 0? Well, this is the amount of the string that's consumed between the time when Q is visited for the first time and when Q is visited the second time. And this is a DFA. There are no epsilon moves. Okay? So something has got to get consumed in Y. Some part of the string is actually being processed or consumed in this part of the computation. So Y is greater than 0. Okay? And XY is less than or equal to P. Well, again, this is where being so precise, you have to pay attention to these little plus or minus 1 details, which is like programming. I hate programming because you have to pay attention to all those little details or your program doesn't work. Mathematics, sometimes you have to pay attention to little details too, but as much as possible you try to get the big idea and not have to worry about those little details. And if they just... Anyway, that's a rant. Okay, is it true x, y less than or equal to p? That is, the length of these two things, these two strings together, the x part and the y part, is less than or equal to p. Yes. Okay. Anybody want to tell me why? Yeah.
We already agreed that you have to have that first loop occur within the first p transitions, and the first loop, like all the string read up to that point, consists of x concatenate y. If that's all within the first p transitions, then x concatenate y has to be less than or equal to p.
Okay. Yeah, I think you've said it right. Let me try to do it. The loop happens within the first p transitions. Okay? The first p transitions means strings of length at most p minus 1. Okay? So xy is a string of length at most p minus 1. Well, if it's a length of string of length at most p minus 1, it's certainly less than or equal to p. That logic is I'm probably off by 1. in that logic somewhere. But hopefully everybody gets it, and you can get the precise plus or minus 1 that I'm missing by reading the book or thinking about it yourself, or at least understanding why that's an issue. Okay, I mean, why? Okay, let's try it again. The looping happens within the first P transitions, because if you go to P transitions means P plus 1 states. There are only P states, so if you go through P plus 1 states, you have to repeat something. Okay, so this happens within the first P minus 1 transitions. P minus 1 transitions means P minus 1 characters. Okay? P minus 1 characters means that the length of x followed by the length of y is at most P minus 1, which certainly means it's less than or equal to P. So that sounds right to me, but then I'm wondering, why did they write this as P and not P minus 1? Yeah?
You said P transitions is P minus 1 characters, but it should be the same. P transitions should be P characters, right?
P transitions should be P characters, yes, right. But this is P plus 1. This is, if you get the idea and you're worried about the plus minus 1, go home and, like writing a program, figure out those little details. It's just, I wish they had written this, yeah.
No, I was going to say, is you kind of transition as entering a state or leaving a state?
A transition, I count a transition as going along an edge.
Okay. Would you consider the edge that goes into the starting state of transition?
The edge that does what?
That goes into the starting state.
No, I don't call that a transition. The edge is going into the start state, yeah.
I think we use P plus 1 over there, so I think you're using P, so it should be P minus 1 in your case, I think.
Okay, so are you with me or against me? I don't.
With you.
Okay, good. One vote for me. All right, so let's consider this proved, and if you're worried about the plus minus 1, good. Think about it yourself and make sure you're, but also realize that you could have written this in a way that it doesn't, that issue of plus minus 1 doesn't even come up. Just make your bounds big enough, and you can always still apply the lemma appropriately. But okay, so the proof of this pumping lemma is just basically what we did over here without reference to any particular language or any particular string. We're just saying that the language is regular and the string is long enough. Okay? And then we're fine. We end up proving this. Okay? So that's the pumping lemma. And now how do we use it when you want to prove that various languages are not regular? So, for example, that language. Oops. Well, we've seen that's not regular, but now, if we already know the pumping lemma, we don't have to go through all these little details. We don't have to go through the actual derivation based on the language, because it's all done abstractly once and for all in the pumping lemma. So I want to prove, I claim this language is not regular. Okay? Well, the pumping lemma says that if you take any string in that language, if it's long enough, then the following things has to happen. Okay? So let's take S equals 0 to P plus 1, 1 to the P plus 1. Okay? Well, is S greater than or equal to P? Definitely. All right? And now we don't even have to say what P is. Before we said P was the number of states. In our specific proof that this language was not regular, before we saw the pumping lemma in general, we said let P be the number of states in the machine that accepts this language. Now we're just saying the pumping lemma tells me that there's some magical P that has this property. So whatever it is, I'm going to take this string. And is it true, do I satisfy the conditions of the pumping lemma? S is an A, yep, because it's got, this is my A, well now we call it B, but all right. S is in this language, yes, because it's some number of zeros followed by some number of ones, the same number of ones. The length of S is greater than or equal to P, definitely. Okay, no problem there. And the pumping lemma tells us the following thing. For any I, S can be written in this, S can be written in this way, such that third of all, xy is less than or equal to P. Okay? So S equals xyz, but this part has length less than or equal to P, so we know that xy just has zeros. In fact, y, is just zeros. Okay? So that's from 3. Y is greater than 0, so it does really have some zeros, just zeros, and at least 1 0, at least 1 0, not empty. And for all I, x, y to the I, z is contained in A. Well, we want to come to the contradiction here, okay? We want to run to a contradiction. We've assumed, we've started out, I didn't write it here, but assume B is regular. Okay, so we have that. Now I want to run to a contradiction. I want to. The pumping lemma says that x, y to the I, z is also in the language. And I want to run to a contradiction to say, no, that can't possibly be. That's not true. The pumping lemma lets me take any I like, because it says it has to be true for every I. Okay, which I is useful? Or let me put it around the other way. Which I is not useful? 1. Yeah, 1 and 0 are not useful. The lemma says that if I is anything, then xyi to the z, xyiz is an A. Well, if I take I equal to 1, then I have xyz, which is S, which we assumed was an A. So I didn't get anywhere. Okay? But I'm just pointing out that you have to engage your brain when you do this. If I did I equals 0, then I have xz. Okay? Do I know? Actually, xz would work. Yeah, I equals 0 would work. That'll be a homework question. But what other I will work?
Anything above 2?
Anything, yeah, 2 or above. And we used 2 earlier. We could have used 3, we could use 7, 17, whatever. Okay? So it looks like the only bad I to pick is 1, I equal 1. I equals 0 actually works, too. Yeah, I got to remember that. I equals 0 homework. Okay. All right. So that's how a proof. And then you get. But x y squared z has more zeros than 1s. So x y squared z cannot be in that language B. But the pumping lemma says it must be in that language. So therefore, we run to a contradiction. Therefore, B cannot be regular. So anyway, this is how you would do the proof that 0 of the n, 1 of the n is not regular once you've established the pumping lemma. And the key point here is that you have to, of course, verify all of the conditions in the pumping lemma hold for this language, and you have to then pick a particular S such that when you apply the pumping lemma, you can run to a contradiction. And when you pick a particular S and then you pick a particular I, if you can get to a contradiction, then you can conclude that the assumption that A was regular, or in this case B was regular, is false. All right? But you have to pick S appropriately, which means sometimes cleverly, and you have to pick I appropriately, which means sometimes cleverly. Okay? It's not true that whatever S you pick in A and whatever I you pick in A, that you're going to run to a contradiction. Okay? So, everybody see that? This says that if A is regular, you get all these things, these nice consequences. It doesn't say that when A is not regular, you don't get these consequences. Okay? So, you have to pick S and I appropriately. But you only need one S and one I to finish a proof by contradiction, because the pumping lemma says that for any S, as long as it's long enough, and any I, then X, Y to the I, Z should be in the language. Okay, I know that's very abstract. The pumping lemma is one of the hardest things to understand. I think if it had never been invented, we'd be fine. We could use, specific arguments like this. Every time we wanted to prove a particular language was not regular, we just come up with an argument like this on that particular language. But, being mathematicians, after a while, you see, hey, those arguments are all awfully similar. Let's step back a ways and generalize from all of those particular arguments and say what's happening in general, and then put it into a more abstract framework like the pumping lemma. Okay? But when you just learn about this with the pumping lemma the first time, if we hadn't gone through a particular example first, then it can be really overwhelming. Just say, we've got this pumping lemma, and here's how you use it to prove that languages are not regular. Okay. Let's take another language. C. C equals a set of strings over 0 star. No, sorry. All right, let's do it this way. W such that W has the same number of zeros and ones. Okay? So it's just binary strings where however many zeros it has the same number of ones. It doesn't have to be all the zeros come before the ones. They can be interspersed any way you like. It's just that the number of zeros and ones has got to be the same. Okay? Is this regular? Take 10 seconds and think about trying to find a DFA that would accept that. Anybody got one? Good. There's not supposed to be any. Okay, we want to claim C is not regular. And we're going to prove this by the pumping lemma. But before I do that, I want to point out that as you build more tools, as we have more and more tools in our tool belt, you can come up with streamlined, clever proofs that don't require going back to the basics, or going back to anyway. You have more tools available to you. So, for example, we know that regular languages are closed under intersection. We know that regular languages are closed under union, and so on. Okay, take two regular languages; their intersection's got to be regular. All right, so here we can come up with a very streamlined proof that doesn't use the pumping lemma, but uses some of the tools that we have available. So if C is regular, then so is, well, D intersects C, where D is the set of W 0 star 1 star. Okay? So this is the set of strings that have some number of zeros followed by some number of ones. Is this regular, by the way? No, I mean this, just D by itself. Is D regular? I see two people shaking no. You're generally good over there, but why are you saying no?
We just proved it.
But this is 0 to the star. It's any number.
Regular expression.
Not the same number. Just any number of zeros followed by any number of ones. Okay? Well, that's certainly regular. You know, you're just taking zeros and then you move over and take ones. Okay? And it's a DFA. Okay? So this is definitely regular. D is regular. Okay? But if C is regular, then so is D intersects C, because regular languages are closed under intersection. But what is D intersects C? What's the set of all strings where it's some number of zeros followed by some number of ones, and it's the same number of zeros and ones? That's the language B. B equals D intersects C. Or maybe I'd put it the other way around. D intersects C equals B. Okay, that's what the language B is. It's the set of all strings where all zeros come before ones, and the number of zeros and the number of ones is the same. But we've already proven that B is not regular. D definitely is regular, so it must be that C is not regular. But D is regular, B is not, so C is not regular also. Okay, so that's what I mean by a proof that uses tools in a clever, interesting way, or clever, short-cutted way, efficient way. And as you build up more and more tools, you can do proofs like this if you happen to see them. Okay, but a more mechanical thing to do is to prove this by applying the pumping lemma. Okay, so a second proof by the pumping lemma. Okay, so we suppose, or it's by contradiction, but the proof will use the pumping lemma. Suppose C is regular, and well, here we're going to pick S, but as I said, when you try to come up with a proof by contradiction using the pumping lemma, you have to pick S in a sort of clever way, and you have to pick I in a sort of clever way. And what we want to do is apply the pumping lemma to that S and that I to come up with a contradiction. And that contradiction then with that contradiction, we can conclude, in fact, that C is not regular. So knowing what the pumping lemma is, and knowing what we're trying to prove that this is not regular, same number of zeros and ones, what S do you think we should use? Anybody have a guess, a hint? Well, how about 0 to the P, 1 to the P? Okay. I mean, it's just a good guess because we've been looking at problems like that. We've been looking at that language. Okay, language that has strings in it like that. So that's definitely, S is definitely in C, right? Okay. Same number of zeros as ones. Okay. So that's a good guess as a start. We'll see if we can make it work. Okay, then then S equals X, Y, Z given by the pumping lemma, okay? As we know, we can break up, since S is in C, and C is assumed to be regular, and S is long enough, pumping lemma says that we can break up X, Y, Z, we can break up S into X, Y, Z, okay, such that xy is less than or equal to p, okay? So y consists only of zeros. But the pumping lemmas, but by the pumping lemma, xy squared z is supposed to be in the language C, okay? But clearly that can't be true. But xy has only zeros, xy squared has only zeros and has length greater than z, so it has more zeros. So xy squared z has more zeros than ones. Contradiction, which means that our initial assumption that the supposition that C is regular can't be true. So we assumed that C is regular, we picked a particular S, we applied the pumping lemma, we saw first of all that the conditions of the pumping lemma are held, that is S is in the language, and that S is long enough. So then the pumping lemma says these conditions should hold, but then we said, but if that's true, since we can observe here that y only contains zeros, xy squared only has zeros, and xy squared, so all the ones are in z, all right? But xyz had the same number of ones and zeros, so xy squared has got to have more zeros than ones. Okay? So we ran into this contradiction, which means that C is not regular. Okay. Now what if we had taken, suppose in this proof we had taken S to be 0, 1 to the p. Okay? We pick a particular S. Is S in C? Same number of zeros and ones, right? Okay, so S was in C. C is this language that has the same number of zeros and ones. And this is 0 followed by 1, p times. So same number of zeros and ones. Is the length of S greater than or equal to p? Yes, okay? So according to the pumping lemma, S can be divided as x, y, z, where xy is less than or equal to p, okay? But now we don't know that y only consists of zeros. We can't conclude that. That's just not something we know anymore for this particular string, all right? The pumping lemma says that xy squared z is contained in C. But now we don't really know much about y. Okay? So what? So xy squared is contained in C, and we don't have this part anymore. Xy squared only has ones. Okay? So all I'm pointing out here is that if you pick this as your S, you can apply, of course, the pumping lemma, you get your various conclusions, but you don't get a clear contradiction. It just wasn't a convenient S to pick so that you ran into a contradiction when you applied the pumping lemma. And yet this S definitely is in this language, C, which is not regular. So why didn't we get a contradiction? Because you don't need to have a contradiction on every S. The pumping lemma says that if S is in the language, you get these various consequences. If S is in that regular language, you get the various consequences. But it doesn't say that when you take an S that's not in a regular language and you apply those statements from the pumping lemma that they'll definitely be false. Okay. It doesn't say you'll always run into a contradiction. It says that when A is a regular language, these always hold. So therefore, if you can find even one string in that claimed A for which this doesn't hold, then you know A is not regular. Okay? So when we started out with 0 to the P, 1 to the P, we were able, that's a particular string, which when we apply the pumping lemma, we get a contradiction. It doesn't mean that we'll run to a contradiction in everything, in every string that's in that language. Okay? All right, I know I can see by the glaze in people's eyes that you either have gotten this or you're not going to get it until you think about it at home. And I'm not doing any good by repeating it. Okay, so the book has more examples of using the pumping lemma. It also has sort of a nice, acute example at the end of that chapter on pumping lemma where he talks about something about pumping down instead of pumping up. Okay, but I'll let you read that. So I think this is enough about the pumping lemma. And if you understood the first proof that I gave, that 0 to the n, 1 to the n is not regular, you will understand the essence of what the pumping lemma is trying to do, even if you don't fully see how to apply it technically on each of those cases. Okay, so read that, the chapter. All right, now I want to change, I'm going to the next chapter, and so we finished regular languages. We'll come back to them. They come up again and again throughout the course in various ways. And it's sort of the initial building block. Finite state machines, non-deterministic finite state machines in particular, are building block on what we're going to do for the rest of the course. But the specific chapter on regular expressions is finished, except I do want to mention one. There's always more, of course. I should have mentioned one thing, or the book should have mentioned. There's a very famous result about, and useful result about regular languages that the book doesn't include. And if we have time towards the end of the course, which we never do, I'll come back to it, which is that there's a whole theory about minimizing the number of states in a finite state machine. So we've seen various languages where you come up with some finite state machine, it has some number of states. Somebody else comes up with another finite state machine, it has fewer states or it has more states. You have different machines with different numbers of states. Okay? If you can imagine, for a particular language, for a particular regular language, imagine the set of all finite state machines that recognize that language. Okay? There's one that has the fewest number of states. And there's actually a constructive algorithm that can find that finite state machine with a minimum number of states. And I've also said the finite state machine. It is unique. So for every regular language, there is one finite state machine that minimizes the number of... Actually, I probably said that too strong. Maybe there's some ties. But anyway, the procedure gives you one finite state machine that minimizes the number of states used. And it's useful at times to take a big finite state machine that's not minimal in that sense, and constructively find the finite state machine, the unique finite state machine that minimizes the number of states given by that algorithm. So the book doesn't include it, so we're not going to do it. But if we have time at the end of the course, I'll come back to that. I'll find some material on that and just pass that out. But it's useful to know because that's possible, because it comes up sometimes in the design of circuits and design of other things that are represented by finite state machines, where you want a small number of states. Okay. The next chapter starts talking about context-free languages, CFLs. I don't think normally these are talked about in this class, but I think they're very important, and I wanted you to have a little bit of exposure. Maybe not 20 minutes is enough, so we might talk about them again, but not much more than like a half a lecture on context-free languages. Okay, so when we talk about context-free language, so we've talked about regular languages, and we've seen that there are actually some languages that are not regular. Well, now we're going to look at a superset, context-free languages. This is a set of languages which contain the regular languages and strictly contain it. There are some, for example, 0 to the n, 1 to the n. That language, which we just showed is not regular, is a context-free language. Okay? And actually, there's a whole hierarchy of languages, a famous hierarchy called the Chomsky languages, that goes from the regular languages, the context-free languages, to something called non-context-free, and then the outermost ring, I've forgotten what it's called in terms of languages, but it's the set of languages that are recognized by Turing machines, and we're going to definitely get to that. Oh, that reminds me, Turing, yes. How many people have looked on the class website recently and noticed that we have homework, solutions to homework 1 is posted? One person, 2 people, 3 people. Okay, solutions to homework 1 that Sean wrote out are posted on the class website. All right, but I put them in a password-protected subdirectory because I didn't want them to get Googled up, which diminishes the long-term value of the book if solutions to homeworks from the book are plastered all over the internet. So if you look at the class website, you will see that I've told you what the ID is that you need to get into that subdirectory, and also what the password is. And the password is Turing, capital T-U-R-N-I-G, Turing. Yeah, it's a name. But it's written there. It's written there on the class website. And anyway, I'll take that down after a little while. I mean, the message that tells you where it is. I don't think Google's smart enough to be able to interpret what I wrote there and then use it to get into the subdirectory, but some person is. All right. Anyway, so we have regular languages and we have context-free languages. Okay, context-free languages are typically defined by a grammar. A context-free language is defined by what's called a grammar. Okay? And a grammar consists of productions or rules defined over 2 alphabets. Two alphabets. One is the normal alphabet. Sort of the normal alphabet that you're used to, and these are now called terminals. The symbols in here in sigma are called terminals. And that really means this is the set of symbols that are going to be used in the input strings, if you want to think of an input string. And then there's another alphabet, R. No, that's not what we call R. That's not what we call. There's another alphabet, V, which is the alphabet of variables. Okay, so let me just give you an example. And then, as I said, there are rules. Here is a rule. 0, A1, B, A goes to B, and B goes to... Okay, so this is a set of productions or rules. Okay, the terminal alphabet in this case is 0, 1, number sign. So those are the terminals. The variable alphabet are A's and B's. And we also, well, in a minute when I show you how to use this, we need to know what a start variable is. But let me just point out here that in these productions or in these rules, what you see on the left side is one variable. So this is one variable. And what you see on the right side is a string that consists of it's a string over those two alphabets. It has some symbols from the terminal alphabet. It has a single symbol from, well, in this case, it has a single symbol or a terminal from the variable alphabet. So this, just in general, let's call this now strings of terminals or variables. But we're going to constrain that in order to get the regular language, to get the context-free languages. Okay, so but this is generally what a grammar looks like. Variable, and the production rules, variable going to some string that has terminals and variables. Here's just a terminal, here's just a variable, here's just a terminal. Okay? And how do you use this? How do you use a grammar? So grammars are used to generate strings over the terminal alphabet. So in the case of finite state machines, we always were thinking of, we have a string coming in, and we have the finite state machine that's processing the string, consuming it, and either accepting or rejecting it. And we'll also have that viewpoint eventually for context-free languages also. But we're starting out with a different kind of viewpoint, which is how do you generate strings that are in a context-free language. Okay, so we're talking about generating strings, and you generate strings through a grammar. And so the grammar, you apply a series of these rules, or the productions. Okay, so to create or generate a string in the language generated by the grammar, and let's give a name to the grammar, G. So here's a particular grammar, G. To create a string in the language generated by the grammar, we need to know where to start. And it's always good to start at the beginning. And when you get to the end, stop. Okay. Where's that from, by the way? I think it's Alice in Wonderland. All right. So in a grammar, we also want to specify the starting variable. So S is some variable in V. It's a variable in V, which is called the starting variable. Okay. So in this example, A is going to be the starting variable. And when you generate a string in this language, you start with the starting variable and you successively apply rules until what you've generated is a string over the terminal alphabet. So you apply rules until the generated string is a string in sigma star. Okay? Let's do an example. So A, well, what does A generate? A generates, if you use this rule, it generates 0A0. And we'll write that down this way, 0, A, 0. Okay? So what we've just generated starting from the start variable A, we've generated 0A0. Yeah?
It's not a 1.
Oh, sorry. 0A1, thanks. 0A1. Now, with this A, we can apply either this rule or this rule. Okay? Let's say we apply this rule again. So this A generates 0A1. And maybe we'll do that again, which generates 0A1. Yeah, we can do it again. 0A1. And now maybe we'll use A generates B. Okay? So A generates B. And B, the only thing we can apply here is B generates the hash. And so what we've generated is a string now that only contains terminals. So this is a string in sigma star. And so what we say is that the grammar generated this string, or this string is in the language that's generated by the grammar. Okay? And that's that. So grammars generate strings from the terminal alphabet by successively applying the productions, successively applying some series of productions until you only have terminal strings, the terminals in the string. Now, notice that there are choices. This is, in a sense, non-deterministic. You don't always, it isn't always true that there's only one choice for a particular variable, which rule you can apply. There can be multiple choices, as we see here. We have two choices for A. So definitely, you can have choices here, and the set of strings that can be generated by this grammar, in this case, because of this particular grammar, is infinite, right? There's no bound on how many times we apply this this production. Okay, but if you looking at that particular example and then looking at this grammar, you might be able to characterize, at least in English, what is the set of all strings that this grammar generates. Can anybody see that? Yeah.
So 0 to the n pound sign, 1 to the n.
Yeah. Okay. So G generates the language W, where W is equal to 0 to the n, pound, 1 to the n. Okay? Yeah. All right. So this is very similar to 0 to the n, 1 to the n. And actually, I'll modify the rules next time. I'll formalize and somewhat modify what we're permitted to do in the productions so that we can actually get the language 0 to the n, 1 to the n. And then you'll see that that language, which isn't regular, is generatable by a grammar. And that, when I define particularly what a context-free grammar is, then you'll see that this language, which is not regular, is context-free language. Okay. So what I want to do next in the context-free languages is turn around to the viewpoint we're used to. We're used to having a machine which can take in input, process it, and then either accept it or reject it. And we're going to develop a machine which is called a push-down automaton, which is like a non-deterministic finite state machine. It's very similar to an NFA, but it has some additional gizmo. And if it didn't have an additional gizmo, then we know that it would just be, it wouldn't be any more powerful than the NFAs that accept regular languages. And so it wouldn't be able to accept this language or recognize this language. So next time we'll continue on with context-free languages and grammars and gizmos and all that.